Zeno's Dichotomy Paradox, the impossible journey. Imagine you want to walk across a room. It seems simple enough. You take a step, then another, but think about it differently. Before you can cross the entire room, you must first cross half the distance. And before you can cross that remaining half, you must cross half of that distance, a quarter of the total room. And before you cross that quarter, you need to cross half of it, an eighth of the total. This goes on forever. You must always cover half the remaining distance before you cover the whole remaining distance. You face an infinite number of halfway points, an infinite sequence of tasks. Logically, it seems you can never actually reach the other side. To complete an infinite number of steps, even infinitesimally small ones, seems impossible in a finite amount of time. And yet you can cross a room. We do it all the time. We reach destinations. We complete journeys. So where does the logic break down, or is our experience of motion an illusion? This is one of Zeno's famous paradoxes, the Dichotomy Paradox. It puts our intuitive understanding of space, time, and motion against a seemingly impeccable logical argument. The ancient Greeks wrestled with this. Does it mean movement itself is impossible? That reality is fundamentally static and our perception of change is flawed? Or does it reveal something profound about the nature of infinity? Mathematicians, centuries later, offered a potential resolution through the concept of convergent series in calculus. They showed that an infinite sum of progressively smaller numbers can, indeed, add up to a finite total. Think 1/2 plus 1/4 plus 1/8 plus 1/16 and so on. This sum gets closer and closer to 1, and at infinity it reaches it. So the infinite number of steps can be completed in a finite time, because each subsequent step takes exponentially less time to complete. Our mathematical tools seem to rescue our experience. But the paradox lingers, doesn't it? It forces us to confront the gap between abstract logic and lived reality. It whispers about the strangeness of infinity, how it behaves in ways our finite minds struggle to grasp intuitively. It reminds us that even the simplest actions, like crossing a room, can hold layers of complexity and wonder when we look closely enough. It's a gentle nudge towards humility, acknowledging that our logical frameworks might not perfectly map the territory of reality. As you settle deeper into relaxation, let that thought drift. The seemingly simple can be infinitely complex. The seemingly impossible can be everyday reality. Hilbert's Paradox of the Grand Hotel. Imagine a hotel with an infinite number of rooms, numbered 1, 2, 3, and so on. And imagine that, remarkably, the hotel is completely full. Every single one of the infinite rooms is already occupied by a guest. Now a new guest arrives seeking a room. Can the hotel accommodate this new guest, even though it's already full? In a finite hotel, if all rooms are full, you simply cannot accommodate anyone else. But Hilbert's Grand Hotel operates under the peculiar rules of infinity. The clever hotel manager says, "No problem." He asks every current guest to please move from their current room, from room N to the next room, room N+1. The guest in room 1 moves to room 2. The guest in room 2 moves to room 3. The guest in room 3 moves to room 4. And so on for all the infinite guests. Since there is no last room as infinity goes on forever, every existing guest finds a new room. This process frees up the first room, room 1, which is now vacant. The new guest can happily check into room 1. So the hotel, despite being completely full, was able to accommodate a new guest. But it gets stranger. Suppose later a bus arrives carrying an infinite number of new guests, numbered 1, 2, 3, and so on. Can the completely full hotel accommodate this infinite influx? Again, the manager smiles. Certainly. This time he asks every current guest to move from their current room, from room N to room 2N. So the guest in room 1 moves to room 2. The guest in room 2 moves to room 4. The guest in room 3 moves to room 6. And so on. This move clears out all the odd-numbered rooms, 1, 3, 5, 7, and so on. An infinite number of rooms are now vacant. The new guests from the infinite bus can now check in. New guest 1 goes to room 1. New guest 2 goes to room 3. New guest 3 goes to room 5. And generally, new guest K goes to room 2K-1. Everyone has a room. The hotel, which was full, accommodated one new guest, and then later accommodated an infinite number of new guests. What does this paradox demonstrate? It illustrates the counterintuitive properties of infinite sets. Concepts like full or having no more space behave very differently with infinite quantities compared to finite ones. Hilbert used this paradox to show that some infinite sets have the same size as proper subsets of themselves. The set of all positive integers has the same cardinality as the set of all positive integers greater than 1 as shown by the first scenario. It also has the same cardinality as the set of even positive integers as shown by the second scenario. This violates our intuition based on finite sets, where removing an element always makes a set smaller. With infinite sets, you can map the elements one-to-one even after removing elements or taking only a part of the set. This property is actually a defining characteristic of infinite sets. The paradox isn't a logical contradiction in the mathematical sense. It's a demonstration of how infinite sets behave differently from finite ones, challenging our deeply ingrained intuitions. It highlights that we cannot simply extend rules and expectations from the finite world directly into the realm of the infinite. Hilbert's Hotel is a playful yet profound entry point into the mathematics of infinity, developed by Georg Cantor. It forces us to confront the idea that infinity is not just a very large number, but a different concept altogether, with its own consistent, albeit strange, rules. Think about the concept of infinity in other contexts. Infinite space, infinite time, infinite possibilities. Our minds struggle to grasp true infinity, often falling back on finite analogies. Hilbert's Hotel serves as a reminder that the infinite operates on a logic beyond our everyday experience. It's a glimpse into the abstract beauty and strangeness of pure mathematics, where concepts can be explored for their logical consistency, even if they defy easy visualization or common sense. As you relax, let your mind wander through the corridors of the infinite hotel. Don't worry about fully understanding it. Just appreciate the paradox as a window into a realm where full doesn't mean no more room, and where infinite guests can always find a place. It's a reminder of the vast and often counterintuitive landscape of mathematical thought. The birthday paradox. Imagine you're in a room with a group of people. How many people need to be in that room for there to be a greater than 50% chance that at least 2 of them share the same birthday, ignoring leap years, just the month and day? Most people's intuition suggests a fairly large number. There are 365 possible birthdays, so maybe you'd need half that number, around 183 people, to get a 50% chance. That seems reasonable. But the actual answer is surprisingly small. You only need 23 people. With just 23 people in a room, the probability that at least 2 share a birthday is slightly over 50%. If you increase the group size to 70 people, the probability jumps to over 99.9%. Why is our intuition so wrong here? Our mistake is often in how we frame the question. We might think about the probability of someone sharing our specific birthday. The chances of that are indeed low, which is 1 in 365. But the question is about any 2 people in the group sharing any birthday. We need to consider all possible pairs of people. In a group of 23 people, there are 253 possible pairs. That's a lot more pairs than individuals. It's easier to calculate the probability that no one shares a birthday, and then subtract that from 100%. The first person can have any birthday. The second person has a 364 over 365 chance of having a different birthday. The third person has a 363 over 365 chance of having a birthday different from the first 2, and so on. For 23 people, the probability of all having different birthdays is approximately 0.493, or 49.3%. So the probability that at least one pair shares a birthday is 1 minus 0.493 equals 0.507, or 50.7%. What does this tell us? It demonstrates how our brains struggle with compounding probabilities and exponential growth. We tend to think linearly, but the number of possible pairs grows quadratically. It also shows that coincidences are often much more likely than we assume. Events that seem rare when focused on a specific outcome, like someone sharing my birthday, become much more probable when considering any instance of that type of event occurring within a set, like any shared birthday in the group. Think about seemingly improbable coincidences in your own life. Running into someone you know in a foreign city. Finding out two unrelated friends have the same obscure hobby. The birthday paradox suggests that given enough opportunities, such overlaps are statistically more likely than we feel they should be. It's a reminder that the universe of chance is vast, and patterns can emerge in ways that defy our gut feelings. Understanding it can shift our perspective. It can make the world feel a little more interconnected, perhaps, or simply remind us that our intuition about probability needs calibration. As you relax, think about the hidden probabilities around you, the unseen connections, the surprising likelihood of overlap in a complex system. Let the counterintuitive nature of the birthday paradox be a gentle reminder that sometimes math tells a different story than our initial assumptions. The Monty Hall problem. Imagine you're on a game show. There are 3 closed doors. Behind one door is a car. Behind the other 2 doors are goats. Your goal is to win the car. The host, Monty Hall, asks you to pick a door. Let's say you pick door 1. Now Monty, who knows where the car is, does something interesting. He opens one of the other doors, one he knows has a goat behind it. For example, he opens door 3, revealing a goat. He then turns to you and asks, do you want to stick with your original choice, door 1, or do you want to switch to the remaining closed door, door 2? What should you do? Does switching improve your chances? Intuition often tells us that since there are now only 2 closed doors, the odds must be 50-50. Switching or sticking shouldn't make a difference. Here you are wrong. You should always switch. Switching doubles your chances of winning the car from 1/3 to 2/3. This baffles many people, even mathematicians at first glance. The key lies in understanding the information revealed by Monty's action. Let's break it down. When you first picked door 1, you had a 1/3 chance of being right and a 2/3 chance of being wrong. In case 1, you initially picked the car. If you pick the car in door 1, Monty can open either door 2 or door 3. Both have goats. If you switch, you lose. In case 2, you initially picked a goat. If you picked a goat, say door 1, the car must be behind either door 2 or door 3. Monty knows where the car is. He must open the other goat door, so if the car is behind door 2, he opens door 3. If the car is behind door 3, he opens door 2. In this scenario, which happens 2/3 of the time, the door Monty doesn't open must be the one with the car. Therefore, if you switch, you win. So by switching, you win if your initial guess was wrong, which happens 2/3 of the time. By sticking, you only win if your initial guess was right, which happens 1/3 of the time. Switching doubles your probability of winning from 1/3 to 2/3. The crucial element is that Monty's choice of which door to open is not random. It's constrained by his knowledge of where the car is and his need to open a door with a goat that you didn't pick. This action concentrates the initial 2/3 probability of the unchosen doors onto the single remaining unchosen door. The Monty Hall problem is a powerful lesson in conditional probability and how new information changes odds. Our intuition fails because we tend to reset the probabilities after Monty opens a door, thinking it's now a simple 50-50 choice between the 2 remaining doors. We fail to account for the history of our initial choice and the non-random nature of Monty's intervention. It teaches us to be careful about assumptions and to rigorously consider how information impacts probabilities. Sometimes, information that seems irrelevant, in this case Monty opening a goat door, actually carries significant weight. Think about decisions in your own life. When you receive new information, how does it affect the probabilities of different outcomes? Do you update your beliefs accordingly or stick to your initial assessment? The Monty Hall problem, beneath its game show facade, is a reminder to question our intuitive leaps, especially with probability. It encourages a more deliberate, analytical approach when faced with choices under uncertainty. Let the image of the 3 doors fade. Allow the surprising logic to settle. Sometimes the best move is the one that feels counterintuitive. The Newcomb Paradox. Imagine a scenario involving 2 boxes, box A and box B, and a highly reliable predictor, perhaps a superintelligent AI or a being with psychic abilities. Box A is transparent and always contains $1,000. Box B is opaque. Its contents depend on a prediction the predictor made yesterday. The predictor predicted whether you would choose to take only box B, or whether you would choose to take both box A and box B. Here's the rule. If the predictor predicted you would take only box B, then the predictor placed $1 million in box B. If the predictor predicted you would take both boxes, then the predictor placed $0 in box B. You know these rules. You also know the predictor has an excellent track record, say, 99% accurate predictions in past instances of this game. You are now standing before the boxes. The predictor has already made its prediction and placed the money in box B or not. That action is in the past. You have two choices. The first choice is one boxing where you take only box B. The second choice is two boxing where you take both box A and box B. What should you do to maximize your gain? Two compelling lines of reasoning led to opposite conclusions. Reasoning 1: trust the predictor. The predictor is almost certainly right. If I choose one box, the predictor likely predicted this and put $1 million in box B. Here expected gain is close to $1 million. If I choose two boxes, the predictor likely predicted this and put $0 in box B. I'll just get the $1,000 in box A. Here expected gain is close to $1,000. Therefore, to maximize my expected winnings based on the predictor's accuracy, I should choose only box B. Reasoning 2: the past is fixed. The money is already in box B or it isn't. My current choice cannot change what the predictor did yesterday. The past is fixed. Consider two possibilities for what's already in box B. In first scenario, the box B contains $1 million because the predictor predicted I'd one box. If I one box, I get $1 million. If I two box, I get $1 million plus $1,000. So two boxing is better. Here $1,000,000 versus $1 million. In second scenario, the box B contains $0 because the predictor predicted I'd two box. If I one box, I get $0. If I two box, I get $0 plus $1,000. So two boxing is better. Because here $1,000 versus $0. In either possible state of the world, taking both boxes yields $1,000 more than taking only box B. Therefore, regardless of the prediction, I should take both boxes. This is the dominant strategy. Here lies the paradox. One line of reasoning strongly suggests one boxing. The other line of reasoning strongly suggests two boxing. Both seem logically sound within their own frameworks, yet they lead to conflicting actions. Philosophers are deeply divided on which reasoning is correct. If you believe your choice is truly free and cannot be perfectly predicted, or that backwards causality is impossible, then the dominance principle seems compelling. The money is already there, take the extra $1,000. If you believe the predictor's accuracy implies some form of determinism, or that your decision is somehow correlated with the past prediction in a way that makes the expected utility calculation valid, then one boxing seems rational. You act in the way you expect the predictor wanted you to act to get the $1 million. Newcomb's paradox forces us to confront fundamental questions about decision-making. What does it mean to make a rational choice? Should we maximize expected utility based on correlations, or follow dominance principles based on causal structure? It's a paradox that probes the relationship between our beliefs about the world and the strategies we deem rational. There's no consensus answer. As you rest, let the ambiguity of the two boxes linger. The paradox isn't about finding the correct answer, but about exploring the fascinating territory where logic, prediction, and freedom seem to collide. The Thomson's lamp paradox. Let's explore a paradox involving infinity and time, related to Zeno's paradoxes, but focusing on the state of an object after an infinite sequence of actions. This is Thomson's lamp, proposed by philosopher James F. Thomson. Imagine a lamp with a toggle switch. At time t equals 0, the lamp is off. At time t equals 1 minute, you switch it on. At time t equals 1.5 minutes, you switch it off. At time t equals 1.75 minutes, you switch it on again. At time t equals 1.875 minutes, you switch it off again. You continue this process, switching the lamp at times corresponding to the partial sums of the geometric series 1 plus 1/2 plus 1/4 plus 1/8, and so on. This infinite series converges to 2. So you perform an infinite number of switchings within a finite time interval, specifically within the interval from t equals 1 to t equals 2 minutes. Now the question is, what is the state of the lamp exactly at the moment t equals 2 minutes? Is it on or is it off? Let's try to reason it out. The lamp is switched on at times t equals 1, then t equals 1.75, corresponding to an odd number of steps after the first. The lamp is switched off at times t equals 1.5, then t equals 1.875, corresponding to an even number of steps after the first. At any moment before t equals 2, the lamp has been switched a finite number of times. We can determine if it's on or off by checking if the last switching event made it on or off. But at exactly t equals 2, the infinite sequence of switchings has supposedly been completed. There is no last switching event in an infinite sequence. You can't say the sequence ended on an on switch or an off switch, because for every on switch, there's a later off switch, and for every off switch after the first, there's a later on switch. So is the lamp on or off? It can't be on because it was switched off after every time it was switched on. It can't be off because it was switched on after every time it was switched off after the initial t equals 1 switch. It seems impossible to assign a definite state to the lamp at t equals 2 based on the description of the process. Thomson used this paradox to argue against the possibility of completing an infinite sequence of tasks in a finite time, a supertask. If such a task were possible, he argued, it could lead to contradictory or undefined states like the lamp at t equals 2. How do philosophers and mathematicians respond? Some argue that the description of the scenario implicitly assumes there is a well-defined state at t equals 2, but the process described doesn't guarantee one. The state of the lamp is defined only for times t less than 2. The definition simply doesn't cover t equals 2. Asking about the state at t equals 2 is like asking for the result of a calculation that wasn't performed. Many point out the physical impossibility of the setup. You can't switch a lamp infinitely fast due to physical limitations. So, the paradox might only exist in the abstract realm of mathematics and logic, not physical reality. Within certain mathematical models like non-standard analysis, one might try to formalize the state at the end of the infinite sequence. But standard analysis suggests the state at the limit point t equals 2 is not determined by the sequence of states before it in this particular oscillating manner. The function describing the lamp state does not have a limit as t approaches 2. Thomson's lamp, like Zeno's paradoxes, forces us to confront the nature of infinity, continuity, and limits. Can an infinite process truly be completed? If so, what is the status of the endpoint? The paradox highlights the potential for contradictions or undefined states when we try to apply concepts of last step or final state to processes involving a convergent infinity of actions. It suggests that the state at a limit point isn't always determined by the sequence leading up to it, especially if that sequence oscillates infinitely. Let the image of the infinitely flickering lamp fade. Rest in the quiet understanding that the bridge between finite sequences and their infinite limits can hold surprises. Sometimes, the limit point exists like t equals 2, but the state at that point remains undefined by the process itself. The liar paradox. This statement is false. 4 simple words that have troubled philosophers for millennia. If the statement is true, then it must be false, as it claims. But if it's false, then it must be true, contradicting itself again. Either assumption leads to its opposite, creating an endless logical loop. This simple paradox reveals profound questions about language, truth, and the foundations of logic itself. Can a statement meaningfully refer to its own truth value? Does every meaningful statement need to be either true or false, with no third option? The ancient form attributed to Epimenides of Crete stated, "All Cretans are liars." If Epimenides himself is a Cretan, then a troubling cycle begins. If his statement is true, then he as a Cretan must be lying, which means his statement must be false. But if his statement is false, then not all Cretans are liars, which means Epimenides might be telling the truth, returning us to our starting point. Kurt Gödel later used a version of this self-reference paradox in his incompleteness theorems, showing that any formal mathematical system powerful enough to describe basic arithmetic must contain statements that can neither be proven nor disproven within that system. The implications were revolutionary. Mathematics itself contains intrinsic limitations. Some philosophers have proposed solutions. Perhaps self-referential statements aren't actually meaningful propositions. Others suggest multi-valued logic, where statements can be partially true or neither true nor false. Still others embrace the paradox as revealing fundamental limitations in our concepts of truth and language. As you edge closer to sleep, consider how language both illuminates and constrains our thinking. The liar paradox isn't merely a logical puzzle, but a window into the relationship between language and reality. How the tools we use to describe the world sometimes become tangled in themselves. In the gentle darkness, let your mind explore these boundaries of meaning, where words fold back upon themselves like whispers echoing in an empty room. The Olbers Paradox. Let's turn to a fascinating paradox from game theory and probability, where seemingly disadvantageous situations combine to produce an advantage. This is Parrondo's paradox. Imagine two simple gambling games, Game A and Game B. Both games are slightly biased against you. Playing either game repeatedly will, on average, cause you to lose money. They are both losing propositions in the long run. Here, Game A is a straightforward game where you have a slightly less than 50% chance of winning each round. For example, tossing a slightly biased coin where your chance of winning $1 is, say, 49.5% and your chance of losing $1 is 50.5%. Play this game long enough and you're almost certain to lose money. And Game B is a bit more complex. The rules depend on how much money you currently have. If your capital is a multiple of 3, you play with a very unfavorable coin with only a 9.5% chance of winning $1 and 90.5% chance of losing $1. If your capital is not a multiple of 3, you play with a more favorable coin with a 74.5% chance of winning $1 and 25.5% chance of losing $1. Even though Game B sometimes offers good odds, the terrible odds when your capital hits a multiple of 3 are bad enough to make Game B, overall, also a losing game if played exclusively. Your capital tends to drift downwards over time. So Game A is losing, Game B is losing. What happens if you play these games in some combination? The paradox discovered by physicist Juan Parrondo is that it's possible to devise a strategy of alternating between these two losing games that results in a winning outcome. For example, playing a sequence like 2 rounds of Game A, then 2 rounds of Game B repeated over and over, can, under the right parameters, cause your capital to steadily increase on average. How can combining 2 losing strategies create a winning one? This seems to defy basic logic. The key lies in the interaction between the games and the state-dependent nature of Game B. The outcome of Game B depends on your capital. Alternating games allows you to switch between them strategically, often moving your capital away from the bad state in Game B by playing Game A for a bit, and then taking advantage of the good state in Game B. Think of it like walking on a shifting landscape or ratchet mechanism. Game A might gently push you downhill overall, but it randomly moves you around different positions. Game B has some positions that are very steep downhill and others that are slightly uphill. By switching, you can use Game A to occasionally jump off the steep downhill parts of Game B, and then use the slightly uphill parts of Game B to gain ground before potentially switching back to A. The combination creates a dynamic where the whole is greater than the sum of its parts. The losing nature of each game individually doesn't account for the synergistic effect created by switching based on the capital state implicitly influencing Game B's odds. It's related to concepts like Brownian ratchets in physics, where random motion combined with an asymmetric potential can lead to directed movement. Parrondo's paradox is a powerful illustration that systems can behave in complex nonlinear ways. Simply analyzing the components in isolation may not predict the behavior of the combined system. It has potential implications in various fields like economics or finance, biology, engineering, and others. The paradox challenges our intuitive assumptions about linearity and simple addition. It shows that negative expectations don't always compound. They can sometimes cancel each other out or even reverse when combined dynamically. It encourages us to look for hidden dependencies and interaction effects when analyzing complex situations. Sometimes, the optimal strategy involves embracing variability and switching between approaches, rather than sticking rigidly to one, even if that one seems best on average in isolation. Let the image of the counterintuitive winning strategy fade. Rest in the understanding that systems can hold surprises. Losing parts can combine to make a winning whole, reminding us of the complex and often paradoxical dynamics that emerge from interaction. The Potato Paradox. Let's begin this section with a seemingly simple puzzle involving percentages that often trips up our intuition. It's sometimes called the Potato Paradox. Imagine you have 100 kilograms of potatoes. These potatoes, being vegetables, are mostly water. Let's say, for this example, they are precisely 99% water by weight. So out of 100 kg total weight, 99 kg is water, and 1 kg is solid potato stuff like starch, fiber, and others. Now you leave these potatoes out in the sun for a while and some water evaporates. The amount of solid potato stuff remains exactly the same, which is 1 kg, but the percentage of water decreases. Suppose the potatoes dehydrate to the point where they are now 98% water by weight. The question is, what is the new total weight of the potatoes? Our intuition might suggest the weight only decreased slightly. Going from 99% water to 98% water sounds like a very small change, maybe losing just a kilogram or two. But let's follow the logic carefully. The key is that the solid part, the 1 kg of potato stuff, hasn't changed its weight at all. Initially, this 1 kg of solids constituted 1% of the total weight since 99% was water. Here 1 kg is 1% of 100 kg. After dehydration, the potatoes are 98% water. This means the solid part must now constitute the remaining 2% of the new total weight. So that same 1 kg of solid potato stuff now represents 2% or 1/50th of the new total weight. If 1 kg is 2% of the new weight, what is the new total weight? We can set up a simple equation which is 0.02 times new weight equals 1 kg. Solving for the new weight gives we have new weight equals 1 kilogram per 0.02, which equals to 50. The new total weight of the potatoes is only 50 kilograms. The potatoes lost half their weight just by going from 99% water to 98% water. This result seems dramatically large compared to the small percentage change in water content. Why is our intuition often so wrong here? We tend to focus on the percentage of water, rather than the percentage of the solids which doubled, from 1% to 2% of the total weight. Because the solids are the constant part, their change in proportion dictates the change in total weight dramatically when the initial water percentage is very high. The paradox arises from the nonlinear relationship between the percentage of water and the total weight when the solid mass is held constant. When something is mostly water, even small changes in the water percentage relative to the tiny solid percentage cause large swings in the overall weight. The potato paradox is a great reminder of how percentages can be misleading if we don't consider the base values they relate to. It highlights the importance of focusing on the constant elements in a changing system to understand the true scale of change. Think about situations involving large proportions. A company cutting costs might reduce a tiny expense category by 50%, saving little, but reducing a massive expense category by just 1% could save a fortune. The percentages alone don't tell the whole story. It also subtly touches on how much water influences the properties and weight of many things around us, including ourselves. We are mostly water, and small changes in hydration can have noticeable effects. Let the surprising weight loss of the potatoes settle in your mind. Allow it to be a gentle nudge to look beyond surface percentages and consider the underlying constants and proportions. Sometimes, the most stable element holds the key to understanding the biggest changes. The lottery paradox. Let's consider another paradox that sits at the intersection of rationality, probability, and belief. This is the lottery paradox. Imagine a fair lottery with 1,000,000 tickets. Only one ticket will win. The probability of any specific ticket winning is therefore 1 in 1,000,000, which is extremely low. Consider ticket 1. The probability that ticket 1 will not win is 999,999 over 1,000,000, which is very close to 1 or 99.9999%. It seems perfectly rational, given this extremely high probability, to believe that ticket 1 will not win. The evidence strongly supports this belief. Now consider ticket 2. The probability that ticket 2 will not win is also 999,999 over 1,000,000. So it seems equally rational to believe that ticket 2 will not win. The same applies to ticket 3, ticket 4, and indeed, every single ticket up to ticket 1,000,000. For each individual ticket n, it appears rational to believe the statement ticket n will not win. Here's the paradox: if it's rational to believe ticket 1 will not win, and rational to believe ticket 2 will not win, and so on for all 1,000,000 tickets, then it seems rational to believe the conjunction of all these statements. That is, it would seem rational to believe ticket 1 will not win and ticket 2 will not win, and so on ticket 1,000,000 will not win. But this combined statement is logically equivalent to saying no ticket will win. However, we know for certain that one ticket will win, the lottery is fair, and there is a guaranteed winner. So the statement no ticket will win is definitely false. Thus, the paradox is a set of seemingly individually rational beliefs, when combined, leads to a belief which is known to be false and therefore clearly irrational. How can it be rational to believe each part of a conjunction, but irrational to believe the conjunction itself? This challenges principles like the conjunction principle for rational belief, which states that if you rationally believe proposition P and you rationally believe proposition Q, then you should rationally believe P and Q together. Here is what's going on. High probability is not certainty. One key issue is equating very high probability with justification for outright belief. Perhaps we shouldn't fully believe that ticket 1 won't win, even if it's overwhelmingly likely. Maybe we should only hold beliefs for propositions that are absolutely certain or have a probability of 1. But this seems too restrictive. We hold many rational beliefs based on strong but not conclusive evidence. Belief versus degrees of belief. Perhaps belief isn't a simple yes-no affair. Maybe we should talk about degrees of belief or credences corresponding to probabilities. We have a very high degree of belief that ticket 1 won't win, but not full belief. While each individual credential is high, the probability of the conjunction that all of them don't win is actually 0. Contextualism about belief. What counts as rational belief depends on the context or the stakes. For everyday purposes, believing ticket 1 won't win might be rational. But when considering the set of all tickets and the known structure of the lottery, the standards for rational belief might shift, requiring us to acknowledge the certainty that one must win. Rejecting the conjunction principle. Some philosophers argue the lottery paradox shows that the conjunction principle for rational belief is simply false. It might be rational to believe P and rational to believe Q, but not rational to believe P and Q together, especially when dealing with large sets of probabilistic beliefs that collectively contradict a certainty. The lottery paradox forces us to examine the nature of rational belief, especially in the face of uncertainty and probability. What does it mean to believe something rationally? Does it require certainty or just very high probability? And how do individual rational beliefs combine? It highlights a tension between our intuitive notion of belief as something we accept or reject, and the mathematical reality of probabilities. Think about beliefs you hold based on strong evidence but not absolute proof. Beliefs about scientific theories, historical events, or even everyday occurrences. Are you justified in holding them? What if you hold many such beliefs and there's a tiny chance each is wrong? Could the conjunction of all your beliefs be likely false? The paradox doesn't give an easy answer, but serves as a valuable puzzle for epistemology. It reminds us that the foundations of even seemingly simple concepts like rational belief can be surprisingly complex and perhaps paradoxical. As you drift, let the image of the million tickets blur. Consider the nature of your own beliefs. How much certainty do you require? How do your beliefs fit together? The paradox invites a gentle introspection into the structure of your own understanding. The Braess Paradox. Imagine a simple road network designed to get drivers from a starting point to an end point. Suppose there are two main routes, and the travel time on each route depends on how many other cars are using it. Let's say Route 1 involves a stretch that takes very little time if empty, but gets congested quickly, plus a longer stretch with constant travel time. Route 2 involves a stretch with constant travel time plus a stretch that gets congested quickly. Drivers, acting in their own self-interest, will distribute themselves between these two routes until the travel times are roughly equal. Let's say in this equilibrium, the travel time for everyone is 45 minutes. Now imagine the city planners deciding to improve the network by adding a new super-fast, zero-travel-time road connecting the midpoints of the two routes. This new road seems like a clear upgrade, offering a shortcut. What happens is drivers seeing this new fast connection will try to use it. A driver starting on Route 1 might think, I'll take the first congested part of Route 1, zip across the new fast road, and then take the second constant time part of Route 2, hoping to bypass Route 1's constant part and Route 2's congested part. Similarly, drivers starting on Route 2 might try to use the new road to switch to the second half of Route 1. The paradox, discovered by mathematician Dietrich Braess, is that adding this new road can actually make the travel time worse for everyone. Because everyone tries to take advantage of the new shortcut, they might overload the already congested segments leading to and from the new connection. The new equilibrium, with everyone acting selfishly to minimize their own travel time using the new road, could result in a travel time of, say, 50 minutes for all drivers, longer than the original 45 minutes. Closing the new road would, counterintuitively, improve the overall traffic flow and reduce everyone's commute time back to 45 minutes. How can adding capacity to a network make things worse? Braess's paradox arises in systems where individuals choose their routes based on self-interest, and the performance of a route depends on how many others are using it. Adding a new, seemingly efficient link can change the strategic choices of individuals in a way that leads to a less efficient outcome for the system as a whole. The new road creates new route options that look attractive individually, but fail to account for the collective impact of many people choosing them simultaneously. It disrupts the previous equilibrium in a detrimental way. This isn't just a theoretical curiosity. Braess's paradox has been observed or cited in real-world scenarios, such as traffic patterns in cities like Stuttgart, Seoul, and New York, where closing certain roads or bridges surprisingly improved traffic flow. It also applies conceptually to other types of networks, like computer networks or even electrical grids. Braess's paradox is another compelling example of how individual rationality doesn't always lead to collective optimality. It highlights the complex nonlinear behavior of network systems. It teaches us that network improvements require careful analysis of the entire system's dynamics, not just the local benefits of a new link. Sometimes, what looks like an obvious improvement can have unintended negative consequences due to the interplay of individual choices and system-wide constraints. Think about adding a new communication channel in an organization or a new feature to a software product. Could it, counterintuitively, make things less efficient overall by changing how people interact or use the system? The paradox encourages humility when intervening in complex systems. Our intuition about cause and effect can be misleading when dealing with networks and feedback loops. Sometimes less is more. Sometimes removing an option can improve the outcome for everyone. As you relax, picture the network of roads. Let the paradox remind you that the shortest path for one might not lead to the fastest journey for all. True optimization requires understanding the whole system, not just its parts. The Barber Paradox. Imagine a village where there's only one barber. This barber has a strict rule. He shaves all men in the village and only those men who do not shave themselves. The question is simple: does the barber shave himself? Let's think it through. Suppose the barber does shave himself, but his rule says he only shaves men who do not shave themselves. So if he shaves himself, he violates his own rule. Therefore, the barber cannot shave himself. So suppose the barber does not shave himself, but his rule says he shaves all men in the village who do not shave themselves. Since he is a man in the village and does not shave himself, he must shave himself according to the rule. If he shaves himself, he shouldn't. If he doesn't shave himself, he should. He seems both required to shave himself and forbidden from shaving himself. This is the Barber Paradox, often attributed to Bertrand Russell, though it's a simplified illustration of a deeper problem he identified in set theory. Unlike the Liar Paradox, which deals with truth and language, this one deals with classification and sets, the set of men shaved by the barber. The barber seems to be both inside and outside the set of men who don't shave themselves. How can this be resolved? The most common answer is that such a barber defined by this specific rule simply cannot exist. The conditions defining the barber are inherently contradictory. It's like asking, what happens when an unstoppable force meets an immovable object? The premise itself contains the contradiction. You can't have both in the same universe. So the village, as described with this particular barber and his rule, is an impossibility. The paradox dissolves by showing that the setup itself is logically flawed. But even if the setup is impossible, the paradox is useful. It highlights the importance of precise definitions and the dangers of self-referential definitions in logic and mathematics. It played a role in prompting mathematicians early in the 20th century to be much more careful about how they define sets, leading to more rigorous foundations for mathematics. Think about rules and categories in our own lives. Sometimes we encounter rules or social expectations that seem contradictory. Be ambitious but stay humble. Be independent but be a team player. Be honest but don't hurt anyone's feelings. While not perfect logical paradoxes, they can create a similar feeling of being caught in a bind, where fulfilling one aspect seems to violate another. The Barber Paradox, in its clean logical structure, reflects this tension. It reminds us to examine the assumptions underlying the rules and categories we encounter. Sometimes, the problem isn't in finding the right answer, but in realizing the question itself or the situation described is built on a contradiction. Let the image of the puzzled barber fade. Allow the contradiction to resolve into the quiet understanding that not all descriptions correspond to a possible reality. The Sorites Paradox, also known as the Paradox of the Heap. Imagine a heap of sand. It clearly is a heap, thousands, perhaps millions of grains. Now you remove one single grain of sand. Is it still a heap? Surely, yes. Removing just one grain doesn't change it from being a heap to not being a heap. Now remove another grain. It's still a heap, and another, and another. If you accept that removing one grain never turns a heap into a non-heap, then you can continue this process grain by single grain until you have only one grain left. According to our premise, one grain doesn't make a difference. A single grain must still be a heap. But that's absurd. One grain of sand is clearly not a heap. So where did we go wrong? Which grain was the magic one? Which grain removal suddenly turned the heap into a non-heap? There doesn't seem to be a specific point. This is the Sorites Paradox, from the Greek word soros for heap. It applies to many vague or fuzzy concepts. When does a person become bald? Removing one hair doesn't make a non-bald person bald. When does a collection of people become a crowd? Adding one person doesn't seem to be the tipping point. When does a shade of color stop being red and start being orange? The paradox arises because we have a clear case that a large pile is a heap, a clear non-case that one grain is not a heap, and a premise that small changes don't affect the category. Removing one grain doesn't destroy the heapness. This premise seems true for each individual step, but leads to an absurd conclusion when applied repeatedly. How do we resolve this? There are several approaches, none universally accepted. One approach is to deny the premise. Perhaps there is a specific number of grains, a sharp cutoff point, where removing one more grain makes it cease to be a heap. We just don't know what that number is. This seems counterintuitive, as heap feels like a fuzzy concept, not one with a precise definition. Another approach uses fuzzy logic or degree semantics. Instead of things being absolutely true or false, propositions can have a degree of truth. A large pile is 100% a heap. As you remove grains, the truth value of this is a heap gradually decreases. A single grain has a truth value of 0% for being a heap. There's no sharp line, just a gradual transition. A third approach, contextualism, suggests the meaning of heap depends on the context. What counts as a heap might change depending on why we're asking or what we're comparing it to. The Sorites Paradox highlights the limitations of classical logic when dealing with the vague language we use in everyday life. It challenges our desire for precision and clear categories. Reality, especially as described by human language, is often more blurry than our logical systems want it to be. Think about personal change or growth. When exactly does a student become knowledgeable? When does an acquaintance become a friend? When does practice turn into mastery? There's rarely a single moment, but rather a gradual accumulation, much like the grains of sand. The paradox gently reminds us to be comfortable with ambiguity. Sometimes, the transition is the most interesting part. Let the image of the shifting sand soothe you. Embrace the fuzziness. Sometimes, the lack of a clear line is not a flaw in our understanding, but a reflection of the nature of the thing itself. The Simpson's Paradox. Now let's look at a statistical paradox that can have real-world consequences in fields like medicine and social science. It's called Simpson's Paradox. Simpson's paradox occurs when a trend appears in different groups of data but disappears or reverses when these groups are combined. It sounds strange, but let's illustrate with a hypothetical example. Imagine two hospitals, Hospital A and Hospital B, which are being compared for their success rates in treating a certain condition. Hospital A treated 100 patients, where 80 survived with an 80% success rate. Hospital B treated 100 patients, where 70 survived with a 70% success rate. Looking at the overall numbers, Hospital A seems better, 80% success versus 70%. But now let's break down the data by the severity of the cases they treated. Let's say patients arrived in either good condition or poor condition. For Hospital A, in good condition, 60 were treated and 58 survived with a 97% success, and in poor condition, 40 were treated and 22 survived with a 55% success. It had an overall success of 80%. For Hospital B, in good condition, 20 were treated and 20 survived with a 100% success, and in poor condition, 80 were treated and 50 survived with a 62.5% success. It had an overall success of 70%. Now look closely. For patients in good condition, Hospital B had a better success rate of 100% versus 97%. For patients in poor condition, Hospital B also had a better success rate of 62.5% versus 55%. So Hospital B performed better for both groups of patients, yet its overall success rate was lower. How is this possible? The paradox arises because the groups were of different sizes and distributions. Hospital A treated mostly patients in good condition with 60 versus 40, who have a naturally higher survival rate. Hospital B treated mostly patients in poor condition with 80 versus 20, who have a lower survival rate. The overall average is misleading because it doesn't account for this underlying difference in patient populations. Hospital B took on significantly more difficult cases and performed better within each difficulty level, but its overall average was dragged down by the higher proportion of hard cases. This isn't just a hypothetical curiosity. Simpson's paradox has appeared in real-world data analysis. For example, in studies comparing medical treatments, analyzing university admission rates by gender, or evaluating batting averages in baseball. It shows the danger of relying solely on aggregated data. Looking at overall averages can mask important underlying trends or differences within subgroups. A conclusion drawn from combined data can be the complete opposite of the conclusion drawn from the data when broken down appropriately. Making decisions based on aggregated data without understanding the subgroups can lead to poor choices, like wrongly concluding Hospital A is superior when Hospital B actually performs better given the difficulty of its cases. Simpson's paradox is a cautionary tale for our data-driven world. Statistics can be powerful tools, but they can also mislead if not interpreted carefully. Averages can hide more than they reveal. Context matters. Think about statistics you encounter in the news or online. Are they presenting the full picture? Could there be underlying groups or factors that might change the interpretation if examined more closely? It encourages a healthy skepticism towards broad statistical claims and a desire to dig deeper into the data. It's a reminder that understanding how data is grouped and analyzed is just as important as the final numbers themselves. Let the confusing graphs fade. Rest in the understanding that simple averages don't always tell the whole story. Sometimes the truth lies in the breakdown in the finer details. The two-envelope paradox. Imagine being presented with two sealed envelopes, identical in appearance. You're told that one envelope contains twice as much money as the other. After selecting one envelope, you open it and find $100 inside. Now you're offered a choice, which is keep this $100 or trade for the other unopened envelope. What should you do? Let's reason through it. If the envelope you opened contains the smaller amount, then the other envelope contains $200. But if your envelope contains a larger amount, the other envelope has only $50. Since these two possibilities seem equally likely, the expected value of switching is 1/2 times $200 plus 1/2 times $50, which is equal to $125. Since $125 is greater than your current $100, it appears advantageous to switch. But here's where the paradox emerges. This same reasoning applies regardless of what amount you find in the first envelope. Had you found $1,000 instead of $100, the same calculation would suggest switching for an expected gain. In fact, you could repeatedly switch back and forth, with each switch apparently increasing your expected value, an obviously impossible situation. Where does the reasoning break down? One key insight is that the probabilities aren't necessarily 50-50 once you've seen the amount in your envelope. The true probabilities depend on the distribution of possible amounts, which information we don't have. Another approach recognizes that expected value calculations must consider the full range of possibilities. If the envelopes contain amounts x and 2x, then once you see a value in your envelope, you can determine whether it's x or 2x based on the specific value observed. The paradox arises from treating the unknown value as simultaneously both x and 2x. As sleep approaches, consider how this puzzle illustrates the subtleties of probabilistic reasoning. Sometimes our intuitions about chance lead us astray, and resolving the contradiction requires careful attention to our assumptions and information. The two-envelope paradox reminds us that even simple-seeming probability problems can hide sophisticated mathematical structure. The Ship of Theseus. Imagine the legendary Ship of Theseus, the hero of Athens. It was kept in the harbor for years as a memorial. Over time, the old wooden planks began to rot. To preserve the ship, each rotting plank was carefully replaced with a new, identical one. Eventually, after many years, every single plank, every nail, every piece of the original ship had been replaced. Is the restored ship still the same ship as the original Ship of Theseus? Most people might initially say yes. It occupies the same space, has the same design, and serves the same function as a memorial. It has continuity of form and purpose. But now, imagine someone collected all the old, discarded planks. And suppose they used those original planks to build another ship, assembled in the exact same way as the original. Now we have two ships. Ship A is made of entirely new materials but has the continuity of form and location. Ship B is made of the original materials but has been newly assembled elsewhere. Which one, if either, is the real Ship of Theseus? If you say Ship A is the real one, you prioritize continuity and form over material substance. But then what is Ship B? It's made of all the original parts. If you say ship B is the real one, you prioritize the original material. But then what was ship A during the replacement process? At what point did it stop being the Ship of Theseus? When 50% of the planks were replaced, 90%, or only when the very last original plank was removed? This brings us back to the Sorites Paradox. And what if ship A is the real ship? Then ship B, made of the original matter, is just a copy, even though it has the original substance. This is the Ship of Theseus paradox, a classic thought experiment about identity over time. What makes something, whether an object, an organization, or even a person, remain the same thing despite undergoing gradual change? There's no easy answer. Philosophers have debated this for centuries. Some argue for spatio-temporal continuity. If an object traces a continuous path through space and time, it's the same object regardless of material changes. This favors ship A. Others argue for material continuity. Identity resides in the substance. This might favor ship B, or perhaps suggest that the original ship ceased to exist gradually. Some suggest identity is based on pattern or information, the design and structure. This might also favor ship A. Others argue that identity itself is just a convenient label we apply, a human construct, rather than an inherent property of the object. Perhaps neither ship is truly the original, or perhaps both have a claim in different ways. Now turn this inward. Think about yourself. The cells in your body are constantly being replaced. Over about 7 years, virtually every atom in your body is replaced with new atoms from the food you eat and the air you breathe. Are you the same person you were 7 years ago, 10 years ago, when you were a child? You have the same name, perhaps the same memories, a continuous stream of consciousness. But your physical substance is almost entirely different. Your thoughts, beliefs, and personality have likely evolved significantly. What makes you the same person throughout your life? Is it your body, your memories, your consciousness, your relationships, or your patterns of behavior? The Ship of Theseus paradox doesn't offer an answer, but it deepens the question. It invites us to contemplate the nature of persistence, change, and identity. What does it mean to be you? What parts must remain for you to still be you? As you drift, let these questions float gently. You don't need to grasp a definitive answer. Just appreciate the mystery of continuity in a world of constant flux. The paradox is a mirror reflecting the enduring puzzle of identity itself. The Paradox of Thrift. Individually, saving money seems like a prudent and responsible thing to do. If you save more of your income, you build wealth, gain security, and prepare for the future. If one person saves more, they are generally better off. But what happens if everyone in an economy decides to save more at the same time? The paradox, popularized by economist John Maynard Keynes, is that a collective increase in saving can actually lead to a decrease in total savings and make the economy worse off, potentially harming everyone. Think about the flow of money in an economy. One person's spending is another person's income. If everyone suddenly decides to save a larger portion of their income, they are, by definition, spending less. Less spending means less demand for goods and services. Businesses see their sales decline. In response, they might cut back on production, lay off workers, or reduce investment in new projects. When workers are laid off or businesses invest less, total income in the economy falls. Now, even though people are trying to save a higher percentage of their actual income is lower. A higher savings rate applied to a lower total income can result in a lower absolute amount of savings overall. For example, imagine total income is $1,000 and people save 10%, which is a $100 total savings. If everyone tries to save 20%, spending drops. This causes total income to fall, perhaps to $600. Now, even saving 20% of $600 is only $120. In a more severe downturn triggered by the attempt to save more, total income might fall so much that saving 20% results in only $80 of total savings, which is less than the original $100. So the attempt by everyone to save more simultaneously can lead to a recession and potentially lower overall savings. What is rational and beneficial for an individual can be detrimental when practiced by everyone collectively. This is a classic example of the fallacy of composition, assuming that what is true for a part must be true for the whole. Does this mean saving is bad? Not necessarily. The paradox highlights the importance of context, particularly the state of the economy. In a booming economy near full capacity, increased saving might be beneficial. It frees up resources from consumption towards investment, potentially increasing long-term growth without causing unemployment. But in an economy that is already sluggish or in a recession with unemployed resources, a collective increase in the desire to save can worsen the downturn. The paradox of thrift reminds us that economic systems are complex and interconnected. Individual actions, when aggregated, can have emergent consequences that are not obvious from the individual perspective. It challenges simplistic views about economic virtues. Thrift is generally good, but its collective impact depends on the broader economic environment. Think about other areas where individual rationality might conflict with collective well-being. Driving a car is convenient for one person, but if everyone drives, it leads to traffic jams and pollution. Taking antibiotics for a minor viral infection might seem harmless individually, but widespread overuse contributes to antibiotic resistance, harming everyone. The paradox encourages systems thinking, understanding how individual components interact to create the behavior of the whole system. It suggests that solutions to collective problems often require considering the system level, not just individual actions. As you relax, let this idea of interconnectedness settle. Individual prudence and collective outcomes are not always aligned. Understanding the difference is key to navigating complex systems, whether economic or social. The prisoner's dilemma. Imagine two suspects, Alice and Bob, are arrested for a crime. The police don't have enough evidence to convict them on the main charge, only on a lesser one. They separate Alice and Bob and offer each of them a deal. The deal for Alice is, if you betray Bob and Bob stays silent, you go free and Bob gets 3 years in prison. If you stay silent and Bob betrays you, you get 3 years and Bob goes free. If you both betray each other, you both get 2 years. If you both stay silent, you both get only 1 year. Bob is offered the exact same deal. In this whole situation, they cannot communicate with each other. What should Alice do? Let's analyze her choices from a purely self-interested perspective. She thinks, suppose Bob stays silent. If I also stay silent, I get 1 year. If I betray him, I go free. So if Bob cooperates, I'm better off betraying. Now suppose Bob betrays me. If I stay silent, I get 3 years. If I also betray him, I only get 2 years. So if Bob defects, I'm still better off betraying. No matter what Bob does, Alice's best strategy from her individual perspective seems to be to betray Bob. Bob, facing the same choices and logic, will also conclude that his best individual strategy is to betray Alice. So the likely outcome is that both Alice and Bob will betray each other, and both will end up serving 2 years in prison. Here's the paradox. If they had both chosen to cooperate and stay silent, they would have each received only 1 year in prison, which is a better outcome for both of them than the 2 years they get from mutual betrayal. Rational self-interest seems to lead both individuals to make a choice that results in a worse outcome for both than if they had somehow managed to cooperate. The prisoner's dilemma captures a fundamental conflict present in many real-world situations. Like environmental issues, everyone benefits if pollution is reduced, but each individual or company might find it cheaper to pollute, leading to a collectively worse environment. Another example is price wars. Two competing businesses might be more profitable if they keep prices stable, but each is tempted to cut prices to gain market share, potentially leading to lower profits for both. The dilemma arises because there's a temptation to defect, regardless of what the other player does, because defecting yields a better individual payoff in either scenario. There's a risk in cooperating because if you cooperate and the other defects, you get the worst possible outcome. Mutual cooperation yields a better collective outcome than mutual defection. How can cooperation emerge in situations structured like a prisoner's dilemma? Researchers like Robert Axelrod have studied this using computer tournaments. They found that strategies which are nice, retaliatory, forgiving, and clear tend to perform well in repeated interactions. If Alice and Bob know they will face this situation repeatedly, the possibility of future rewards for cooperation and punishment for defection changes the game. Trust, reputation, and the shadow of the future can make cooperation more rational even from a self-interested standpoint. The prisoner's dilemma doesn't say cooperation is impossible, but it starkly illustrates why it can be difficult, especially in one-off interactions or situations with low trust. It highlights the tension between individual incentives and collective well-being. It forces us to think about the conditions that foster trust and cooperation. Transparency, repeated interactions, mechanisms for accountability, and shared values can help overcome the temptation to defect and achieve mutually beneficial outcomes. As you relax, consider the dilemmas in your own interactions. Where does self-interest clash with mutual benefit? What helps bridge that gap? The paradox serves as a reminder of the delicate balance required for cooperation to flourish. The Fermi Paradox. Named after physicist Enrico Fermi, who famously posed the question during a lunchtime conversation, the paradox highlights a stark contradiction. On one hand, consider the sheer scale of the universe. There are hundreds of billions of stars in our Milky Way galaxy alone. Many of these stars likely have planets orbiting them. Current estimates suggest billions, perhaps trillions, of planets in our galaxy. A significant fraction of these planets might exist in the habitable zone, the region around a star where conditions could potentially allow liquid water to exist, a key ingredient for life as we know it. Life arose relatively early on Earth. If the conditions are right, perhaps life isn't incredibly rare. Given enough time, some life forms might evolve intelligence and develop advanced technology, potentially capable of interstellar communication or travel. The universe is very old, around 13.8 billion years. Our galaxy is also ancient. There has been ample time for intelligent civilizations to arise, potentially millions or even billions of years before us. Given all these factors, the vast number of potential sites for life, the immense timescale, it seems statistically probable that intelligent extraterrestrial life should exist, and that at least some civilizations would have become advanced enough to leave detectable signs of their existence like radio signals, megastructures, probes. On the other hand, the stark reality is, we see no credible evidence. Our searches for extraterrestrial intelligence have found no confirmed signals. We see no obvious signs of alien megastructures or artifacts in our astronomical observations. No verified alien visitors or probes have been detected. The universe appears silent, empty, as Fermi reportedly asked, "Where is everybody?" This is the Fermi Paradox, the conflict between the high probability estimates for the existence of extraterrestrial intelligence and the utter lack of observational evidence. Why the silence? Scientists and thinkers have proposed numerous potential solutions, often grouped into categories. Rare Earth hypothesis. Perhaps the combination of factors needed for complex intelligent life to evolve is incredibly rare. Earth might be a cosmic anomaly. Life might be common, but intelligent life or technological life might be exceedingly scarce. Great filter hypothesis. There might be some universal barrier or challenge that is extremely difficult for life to overcome. The filter is behind us. Perhaps the origin of life itself, or the jump to multicellular life, or the evolution of intelligence was an incredibly improbable step that we somehow luckily passed. The filter is ahead of us. Perhaps civilizations inevitably destroy themselves through technology or hit some insurmountable technological limit before becoming interstellar. This is a more sobering possibility. They exist, but we can't detect them. Too alien, their technology or communication methods might be unrecognizable to us. Maybe they communicate via neutrinos or gravitational waves, or exist in forms we can't comprehend. Too distant, interstellar travel or communication might be vastly more difficult or expensive than we imagine, effectively isolating civilizations. Deliberate hiding. Perhaps advanced civilizations know about us but choose not to interfere, observing us like animals in a zoo or nature preserve. Beyond our comprehension, their existence might be on scales or dimensions we cannot perceive. We are alone, perhaps against the odds. We are indeed the first intelligent, technological civilization to arise in our observable region of the universe. The Fermi Paradox is profound because any potential answer has significant implications for humanity's place in the cosmos. If we are truly alone, it underscores the preciousness and potential responsibility of life on Earth. We might be the universe's only chance so far for self-awareness. If advanced life is common but inevitably destroys itself, it serves as a stark warning for our own future. If they exist but are hiding or undetectable, it hints at depths and possibilities in the universe far beyond our current understanding. The paradox isn't necessarily something to be solved definitively right now, but rather a framework for contemplation. It encourages humility in the face of cosmic scales and uncertainty. It fuels our curiosity to keep exploring, listening, and searching. As you drift towards sleep, let your mind expand to the scale of galaxies. Feel the weight of the great silence. Is it an empty silence or one filled with presences we cannot yet perceive? The question hangs in the vast, quiet darkness. Where is everybody? The Olbers Paradox. Why is the night sky dark? It seems like an obvious question with an obvious answer, because the sun is down. But the paradox arises when you consider the nature of the universe as it was then often assumed, infinite, eternal, and roughly uniformly filled with stars. If the universe is truly infinite in extent and has existed forever, and stars are scattered throughout it, then no matter which direction you look, your line of sight should eventually end on the surface of a star. Think about standing in a truly infinite forest. No matter which direction you look, eventually, your view will be blocked by a tree trunk. Similarly, in an infinite, eternal universe filled with stars, every point in the night sky should be as bright as the surface of a star. Distant stars would appear fainter individually, but there would be more and more stars at greater distances, compensating perfectly for the faintness. The entire night sky should be ablaze with blinding light day and night. But it's not. The night sky is predominantly dark, punctuated by relatively few points of light. So why the darkness? Where does the assumption of an infinite, eternal, static, uniform universe filled with stars break down? The resolution to Olbers Paradox came with discoveries in modern cosmology, primarily related to the Big Bang theory. The universe is not infinitely old. The universe had a beginning approximately 13.8 billion years ago. This means we can only see light from stars and galaxies whose light has had time to reach us within that time frame. Light from stars beyond a certain distance simply hasn't reached Earth yet. The forest doesn't stretch infinitely in time. The universe is expanding. The universe is not static, it's expanding. Distant galaxies are moving away from us, and the further away they are, the faster they recede. This expansion causes the light waves from these distant objects to be stretched, shifting them towards lower energies and longer wavelengths. Extremely distant objects can have their light red shifted so much that it moves out of the visible spectrum into infrared or microwave wavelengths, rendering them invisible to our eyes. The trees in the distance are moving away, and their light is becoming less energetic. Finite number of stars or finite lifetimes. While the universe is vast, the number of stars isn't truly infinite in the observable part, and stars themselves have finite lifetimes. The primary factors resolving the paradox are the finite age of the universe and its expansion. These factors mean our line of sight does not inevitably end on a star surface whose visible light reaches us. There's simply not enough light filling the volume of the observable universe from its finite past to make the entire sky bright. Olbers Paradox, like the Fermi Paradox, uses a simple observation, which is the darkness of the night sky, to probe fundamental properties of the cosmos. The fact that the night sky is dark is actually profound evidence supporting the Big Bang model of a universe with a finite age and ongoing expansion. It transforms a mundane observation into a cosmic clue. The darkness isn't just an absence of sunlight, it's a presence of evidence about the universe's history and evolution. It reminds us that even the most basic features of our experience can hold deep scientific meaning if we ask the right questions. The darkness is not empty. It's full of information about time, distance, and the dynamic nature of reality on the grandest scale. As you rest under the dark sky, appreciate that darkness not as mere absence, but as a testament to a universe that is dynamic, evolving, and has a history. The silence of the Fermi Paradox and the darkness of Olbers Paradox are two sides of the same cosmic mystery, inviting us to contemplate our place within this vast, ancient, and expanding reality. The Raven Paradox. Let's explore a paradox concerning evidence and confirmation in science and logic, the Raven Paradox, also known as the Hempel's Paradox. Consider the statement, "All ravens are black." This seems like a reasonable hypothesis we might want to test through observation. How do we confirm it? Logically, observing a black raven supports the hypothesis. Each time we see a black raven, our confidence in the statement, "all ravens are black," increases slightly. This seems straightforward. Now consider the concept of logical equivalence. The statement, "all ravens are black," is logically equivalent to the statement, "all non-black things are non-ravens." If it's true that all ravens are black, then it must also be true that if something is not black, it cannot possibly be a raven. Conversely, if it's true that all non-black things are not ravens, then anything that is a raven must necessarily be black. The two statements stand or fall together. They mean the same thing logically. Here comes the paradox. If the two statements are logically equivalent, then evidence confirming one should also confirm the other. We agreed that observing a black raven confirms all ravens are black. Therefore, observing something that confirms the equivalent statement, "all non-black things are non-ravens," should also confirm all ravens are black. What confirms all non-black things are non-ravens? Observing any object that is both not black and not a raven. So observing a red apple which is not black and not a raven should logically confirm the hypothesis that all ravens are black. Observing a green shoe which is not black and not a raven should also confirm all ravens are black. Observing a white swan which is not black and not a raven should also confirm all ravens are black. This seems absurd. How can finding a red apple in my kitchen tell me anything about the color of ravens halfway across the world? It feels intuitively wrong that observing non-ravens could confirm a statement about ravens. The principle that finding confirming instances supports a hypothesis, combined with the principle of logical equivalence, leads to the counterintuitive conclusion that observing irrelevant objects like red apples confirms specific hypotheses like all ravens are black. How have philosophers and logicians responded? Some argue that yes, observing a red apple does technically confirm all ravens are black, but only by an infinitesimally small amount. There are vastly more non-black non-ravens than there are ravens. So finding one provides extremely weak evidence compared to finding a black raven, which comes from a much smaller pool of potential counterexamples. Our intuition rebels because the confirmation is practically negligible. Others suggest our initial understanding of confirmation is too simplistic. Perhaps confirmation isn't just about accumulating positive instances. Bayesian approaches, for example, focus on how much an observation increases our belief in a hypothesis compared to alternative hypotheses. Observing a red apple doesn't really help distinguish all ravens are black from most ravens are black or all ravens are purple. Observing a black raven, however, does provide stronger discriminating evidence. Some argue the relevance of evidence depends on the context of the investigation or the testing procedure. If we set out to test the raven hypothesis specifically, finding apples is irrelevant to our chosen methodology. Raven Paradox challenges us to think more deeply about what constitutes evidence and how scientific hypotheses are confirmed. It highlights a potential gap between formal logic and our intuitive understanding of relevance and evidential support. It shows that purely logical relationships like equivalence don't always align perfectly with our concepts of meaningful evidence or efficient investigation. While logically sound, checking apples to confirm raven color is clearly not a good scientific strategy. The paradox encourages us to consider the quality and relevance of evidence, not just its logical relationship to a hypothesis. It prompts questions about how we filter information and decide what observations actually inform our beliefs about the world. Think about how you evaluate claims or beliefs in your own life. What kind of evidence do you find convincing? Do you sometimes encounter information that is logically consistent but feels irrelevant or unhelpful? Let the image of the irrelevant red apple confirming raven blackness gently fade. Appreciate the nuance required in bridging formal logic with the practicalities of learning about the world. Confirmation is a more subtle process than it first appears. The Buridan's donkey. Attributed to the 14th century philosopher Jean Buridan, the paradox imagines a hypothetical donkey that is exactly equally hungry and thirsty. It is placed precisely midway between a bale of hay and a pail of water, both equally accessible and equally desirable to the donkey in its current state. The donkey, being a perfectly rational creature in this thought experiment, analyzes the situation. There is no reason to prefer the hay over the water, nor the water over the hay. Both options are equally good, and the effort required to reach either is identical. Since there is no determining reason to choose one over the other, the perfectly rational donkey finds itself unable to make a decision. It cannot justify turning left any more than turning right. Caught in perfect equilibrium, unable to break the symmetry, the donkey stands frozen in place and ultimately perishes from both hunger and thirst. The paradox highlights a potential problem for theories of choice based purely on rational deliberation and sufficient reason. If action requires a reason, and there is no reason favoring one option over equally good alternatives, how can a choice ever be made? Does rationality inevitably lead to paralysis when faced with perfect symmetry? Of course, real donkeys don't usually starve when faced with two equally appealing options. So, how is the paradox resolved in reality? Rejection of perfect symmetry. Perhaps the premise of a perfectly rational donkey or perfectly symmetrical options is the problem. Real-world agents are not purely rational calculating machines. Emotions, impulses, random fluctuations in attention, or tiny imperceptible differences in the environment can break the symmetry and nudge the decision one way or the other. The donkey might just happen to glance slightly left first, or feel a tiny bit hungrier than thirsty at that exact moment. The random choice. Some philosophers argue this highlights the role of the will or the capacity for arbitrary choice. When reason provides no basis for distinction, the will simply makes a choice, asserting itself without a determining reason. It might be akin to flipping a mental coin. The act of choosing itself becomes the tiebreaker. Recognizing the cost of indecision. A truly rational agent might recognize that indecision itself has a cost: starvation, in the donkey's case. Therefore, the rational choice is simply to choose something, even arbitrarily, rather than remain stuck. The goal isn't necessarily to make the optimally justified choice, but to make a choice that avoids the negative outcome of an action. Subtle differences always exist. Perhaps perfect symmetry is a theoretical abstraction that never truly occurs in the physical world. There will always be some minute difference, a slight breeze, a shadow, an internal physiological flicker that provides a tiny, perhaps subconscious nudge. Buridan's donkey, while a somewhat comical image, probes deep questions about determinism and the nature of rational choice. If every action requires a sufficient cause or reason, how do we explain choices between seemingly identical options? Does it imply an element of randomness or uncaused volition? Think about times you've been faced with choices where the options seemed genuinely equal in value. Choosing between two identical items on a shelf, two equally good job offers, or two equally appealing vacation destinations. How did you decide? Did you find some small distinguishing factor, make an arbitrary leap, or perhaps feel paralyzed for a time? The paradox reminds us that decision-making isn't always about finding the single best or most rational path based on clear reasons. Sometimes, It involves navigating ambiguity, embracing imperfection, or simply making a commitment to act even when justification is symmetrical. It suggests that the ability to break ties, to make a choice even without a compelling rationale distinction, might be a crucial aspect of agency and avoiding paralysis. Let the image of the indecisive donkey fade. Allow yourself the freedom that comes from knowing that not every choice requires perfect justification. Sometimes, simply choosing is enough to move forward. The von Neumann Paradox. Now, let's explore a paradox from the realm of geometry and set theory that truly challenges our fundamental intuitions about area and space. This is a 2D analog of the more famous Banach-Tarski paradox, sometimes associated with John von Neumann. Imagine a simple shape in a two-dimensional plane, like a square or a disk. Intuitively, we believe that if you cut up this shape into a finite number of pieces and rearrange those pieces without stretching or overlapping, the total area must remain the same. You can't create an area out of nothing just by cutting and rearranging. This seems like a basic principle of geometry and physical reality. The von Neumann paradox demonstrates something astonishingly counterintuitive within the framework of modern mathematics. It is theoretically possible to take a shape like a square, decompose it into a specific finite number of highly complex and bizarre point sets the pieces, and then rearrange these sets using only rotations and translations to form two identical copies of the original square. Think about that. One square is cut into pieces, and those pieces are simply moved around to form two squares, each identical in size to the original. It seems to violate the conservation of the area completely. Where did the extra area come from? This paradox, like its 3D cousin Banach-Tarski, hinges on several key mathematical concepts. The axiom of choice. This is a fundamental principle in set theory that allows mathematicians to make an infinite number of arbitrary choices simultaneously. It's needed to prove that such paradoxical decompositions are possible. While powerful and widely used, the axiom of choice has some non-intuitive consequences, this being one of them. Non-measurable sets. The pieces involved in these decompositions are not nice, everyday shapes with well-defined areas. They are incredibly complex fractal-like point sets that are non-measurable. This means the standard concept of assigning an area simply doesn't apply to these individual pieces. They are so intricately scattered and dust-like that they defy conventional measurement. Abstract versus physical. This is a paradox within pure mathematics dealing with abstract sets of points in Euclidean space. It does not mean you can physically take a block of wood, cut it up, and make two identical blocks. Physical objects are made of atoms, not infinite point sets, and they obey physical laws, including conservation of mass and volume. The paradoxical decompositions rely on infinite precision and the strange properties of infinite point sets that don't correspond to physical reality. So the paradox isn't saying area isn't conserved in the real world. It's revealing the surprising and deeply weird consequences that can follow from the foundational axioms mathematicians use to build their systems, particularly the axiom of choice when applied to infinite sets. It shows that mathematical space, as defined by set theory, has properties far stranger than our physical intuition suggests. Concepts like area or volume that seem straightforward might break down when applied to the infinitely complex objects allowed by the axioms. The von Neumann paradox serves as a stark reminder that mathematical formalism, while powerful and consistent, can lead to results that profoundly clash with our everyday experience of space and quantity. It highlights the gap between abstract mathematical possibility and concrete physical reality. It invites us to appreciate mathematics not just as a tool for describing the physical world, but as a realm of abstract structures with its own internal logic, capable of generating wonders and paradoxes that stretch the limits of our imagination. Let the image of the duplicating square dissolve. Rest in the understanding that the infinite depths of mathematical abstraction contain landscapes far stranger than those we navigate daily. The paradox is a glimpse into that abstract wilderness. The Kleene-Rosser Paradox. This paradox arose in the early days of developing formal systems to describe computation, specifically within a system called lambda calculus. developed by Alonzo Church and influenced by Stephen Kleene and J. Barclay-Rosser. Lambda calculus is a very simple, yet powerful, language for defining functions and computation. In lambda calculus, everything is a function. Functions can take other functions as inputs, and functions can produce other functions as outputs. It's a world built entirely of computation itself. The paradox emerged from trying to create functions within this system that could talk about other functions or even themselves, similar to the self-reference we saw in the Liar paradox or Russell's paradox. Essentially, Kleene-Rosser showed that the original formulation of lambda calculus was logically inconsistent. They demonstrated that it was possible within the system to construct a term that behaved like Russell's paradoxical set. They were able to define a function that could effectively ask, does this function when applied to itself result in something specific? This led to a contradiction. If the function did result in that specific thing when applied to itself, then by its definition it shouldn't have. And if it didn't result in that specific thing, then by its definition it should have. The details involve the specific syntax of lambda calculus, including defining logical operations like negation and conjunction within the system, and then constructing a self-referential expression using techniques like the Y Combinator. The upshot was that this paradoxical construction allowed one to prove any statement within the original lambda calculus. If a logical system allows you to prove anything, it's considered inconsistent and not a reliable foundation for mathematics of computation. This was a significant finding because lambda calculus was being explored as a potential foundation for all of mathematics, an alternative to set theory. The Kleene-Rosser paradox showed that this particular foundational attempt, in its initial naive form, failed due to inconsistency, much like Russell's paradox had undermined naive set theory. How was it resolved? The paradox led to the development of typed lambda calculi. In these systems, functions are assigned types, restricting how they can be applied. You can't just apply any function to any other function or itself arbitrarily. These type systems prevent the construction of the paradoxical self-referential terms, restoring logical consistency. Modern programming languages often incorporate type systems inspired by this work to prevent certain kinds of errors and ensure logical soundness. The Kleene-Rosser paradox, while technical, plays a crucial role in the history of logic and computer science. It underscores a recurring theme: naive approaches to self-reference, whether in sets, language, or computation, often harbor hidden contradictions. It highlights the vital importance of careful axiomatization and structural rules in building consistent formal systems. It showed that the very foundations of computation required careful logical construction to avoid collapsing into paradox. As you relax, let the abstract computations fade. Appreciate the paradox as a deep insight from the architects of our digital age. It's a reminder that consistency, the bedrock of reliable reasoning and computation, sometimes requires carefully imposed limits to avoid the pitfalls of unrestricted self-reference. The Schwarz Lantern. Let's turn back to geometry and explore a paradox concerning surfaces and limits, one that challenges our intuition about approximation. This is the Schwarz Lantern, named after Hermann Schwarz. Imagine a simple cylinder. We know how to calculate its curved surface area using a standard formula. Now suppose we try to approximate this curved surface area by inscribing a polyhedron inside the cylinder. A natural approach might be to use many thin, triangular facets, like building a complex folded lantern structure within the cylinder's boundaries. Think of stacking rings of triangles. Each ring consists of triangles whose vertices alternate between two circles on the cylinder's surface, creating a zigzag pattern around the circumference. Let's say we stack many of these rings, making the triangles very narrow vertically. As we increase the number of triangles around the circumference in each ring and increase the number of rings stacked vertically, our inscribed polyhedron seems to get closer and closer to the shape of the cylinder. The vertices of all the triangles lie on the cylinder's surface. Intuitively, we'd expect the total surface area of all these tiny triangular facets to approach the true surface area of the cylinder as we make the approximation finer and finer, using more and more smaller triangles. Here lies the paradox. Depending on how you construct this approximating surface, the total area of the triangles might not converge to the area of the cylinder at all. In fact, Schwarz showed that you can construct such a sequence of inscribed polyhedron whose total surface area increases without bound, approaching infinity, even as the polyhedron visually seems to hug the cylinder ever more closely. How can the area of the approximating surface approach infinity when it seems to be approximating a finite area? The issue lies in the angles of the triangles. In the Schwarz Lantern construction, as you increase the number of rings, the triangles become increasingly tilted relative to the cylinder's surface. They become almost perpendicular to the cylinder wall in the limit. While the vertices of the triangles get arbitrarily close to the cylinder's surface, the planes of the triangles themselves do not align with the tangent plane of the cylinder. Adding up the areas of these increasingly tilted, crinkled facets leads to a sum that diverges. Think of trying to approximate the length of a diagonal line by using only horizontal and vertical steps like on a grid. No matter how small you make the steps, the total length of the staircase path will always be the sum of the horizontal and vertical distances, not the shorter diagonal length. The Schwarz Lantern is a more complex 3D version of this problem with surface area. The paradox reveals that just because a sequence of surfaces converges pointwise does not guarantee that their areas converge. For area convergence, you also need conditions on the convergence of the surface normals. The Schwarz Lantern is a cautionary tale from the world of calculus and geometry. It teaches us that intuition about limits and approximations, especially when moving from lengths to areas or volumes, needs to be rigorously checked. Looking like the target shape isn't always enough. It highlights the subtleties involved in defining surface area for curved objects and the potential pitfalls in seemingly natural approximation methods. It spurred mathematicians to develop more precise definitions of surface area and convergence. Think about approximations you use or encounter. Are they capturing the essential properties correctly, or could they be inadvertently measuring something else due to misalignment or orientation, like the tilted triangles of the lantern? The paradox encourages a deeper respect for mathematical rigor. Our intuition can be a powerful guide, but sometimes, as with the infinitely crinkled lantern approximating a smooth cylinder, it leads us astray. The details of the limiting process matter profoundly. Let the image of the deceptive lantern fade. Rest in the quiet appreciation for the precision required in mathematical description and the surprising ways approximations can diverge from the reality they seem to approach. The St. Petersburg Paradox. Let's explore a classic paradox in probability and decision theory that reveals a stark conflict between mathematical expectation and rational human behavior. This is the St. Petersburg Paradox, discussed by Daniel Bernoulli in the 18th century. Imagine a game of chance offered by a casino. The rules are simple. A fair coin is tossed repeatedly until it lands tails for the first time. If the first tails appears on the keth toss, meaning you got K-1 heads followed by a tails, the casino pays you $2K. If tails comes up on the first toss, you win 21, which is equal to $2. Here the probability is 1/2. If it's heads then tails, you win 22, which is equal to $4. Here the probability is 1/4. If it's heads tails, you win 23, which is equal to $8. Here the probability is 1/8. If it's heads tails, you win 24, which is equal to $16. Here the probability is 1/16, and so on. There's a small chance of winning a very large amount of money if you get a long streak of heads. The question is, how much would you be willing to pay the casino for a single chance to play this game? What is a fair price for a ticket? Standard decision theory suggests the fair price is the expected value of the game, which is the average amount you'd expect to win per play if you played many times. Let's calculate it. The expected value here is equal to $1 plus $1 plus $1 plus $1 plus, and so on. The expected value is an infinite sum of $1. It's infinite. Here lies the paradox. The mathematical expectation of the game is infinite. This suggests that theoretically, a perfectly rational person should be willing to pay any finite amount of money to play this game, even their entire fortune, because the expected return is infinitely large. However, intuitively, most people would only be willing to pay a relatively small amount for a ticket, perhaps $10, $20, maybe $50. Almost nobody would risk their life savings on a single play, despite the infinite expected value. Why the huge discrepancy between the theoretical calculation and rational human behavior? Several explanations resolve the paradox by pointing out limitations in the assumptions. Diminishing marginal utility of money. Daniel Bernoulli himself proposed this. The value or utility of money is not linear. Winning an extra $1 million means less to a billionaire than it does to someone struggling. Doubling your winnings provides progressively less additional happiness or utility. If we calculate the expected utility instead of expected monetary value, and assume utility grows slower than linearly, the expected utility becomes finite, suggesting a finite fair price. Finite resources of the casino. The calculation assumes the casino has infinite funds to pay out any potential winnings, no matter how large. Real casinos have limits. If the casino caps the maximum payout, the expected value becomes finite and often quite modest. Risk aversion. Most people are risk-averse. They prefer a certain smaller gain over a gamble with a higher expected value but also a risk of loss or very small gain. The St. Petersburg game has a high probability of 1/2 of only winning $2 and a 3/4 probability of winning $4 or less. The huge potential payouts have vanishingly small probabilities, and people weigh the risk of a low payout heavily. Ignoring infinitesimal probabilities. Perhaps people intuitively disregard extremely low probability, high payout events when making practical decisions. The chance of winning over, say, $1,000 requiring 9 heads in a row is less than 1 in 500. Finite plays. The expected value calculation represents an average over an infinite number of plays. In reality, you only play once or a few times. The probability of actually realizing a huge win in a limited number of plays is very small. The St. Petersburg Paradox was historically important because it highlighted the inadequacy of using simple mathematical expectation as the sole guide for rational choice under uncertainty. It spurred the development of utility theory, incorporating subjective value and risk preference into decision-making models. It teaches us that rationality in decision-making is more complex than just maximizing expected monetary value. Human factors like risk aversion, the subjective value of outcomes, and the consideration of real-world constraints like finite resources play crucial roles. It also serves as a reminder of the strange properties of infinity. An infinite expected value doesn't necessarily translate into a sensible real-world price, because realizing that expectation involves confronting infinitesimally small probabilities of infinitely large payoffs. Let the image of the infinitely rewarding gamble fade. Rest in the understanding that rational choice involves more than just calculation. It involves evaluating risk, subjective value, and practical constraints. The paradox bridges the gap between abstract probability and tangible human decision-making. Gabriel's horn, the painter's paradox. Imagine an unusual three-dimensional shape, a horn that stretches infinitely in one direction while becoming infinitely thin. This object, known as Gabriel's horn, begins with a circular opening of radius 1 and extends along the x-axis, with its radius at any point given by y equals to 1 over x for x greater than or equal to 1. The fascinating paradox emerges when we calculate the horn's volume and surface area. Despite extending infinitely, the horn has a finite volume which is exactly pi cubic units. You could fill it completely with a finite amount of paint. Yet remarkably, the horn's surface area is infinite. This creates the painter's paradox. You could fill the horn with a finite amount of paint, but you could never paint its exterior surface, no matter how much paint you had available. How can we reconcile these seemingly contradictory properties? The key insight is that as the horn extends toward infinity, it becomes increasingly thin. The rate at which the horn narrows compensates precisely for its infinite length, resulting in a finite volume. However, the surface area grows more slowly than the volume decreases, leading to an infinite total area. This paradox reveals how our intuition about finite and infinite quantities can lead us astray. An infinite object can have finite properties, and quantities that seem naturally related can behave very differently in extreme cases. Gabriel's horn exists purely in the abstract realm of mathematics, yet it illuminates a broader truth. Mathematical reality sometimes defies the expectations we develop from everyday physical experience. The universe of mathematical objects contains wonders that stretch beyond what we can directly observe or even fully visualize. As you drift closer to sleep, imagine this peculiar horn extending toward infinity, becoming ever thinner yet never quite disappearing. Consider how mathematics allows us to precisely describe and understand objects that could never exist in our physical world, yet reveal profound truths about the nature of space, measure, and infinity. The Bertrand Paradox. Imagine a circle with an equilateral triangle inscribed within it. If you were to randomly select a chord of the circle, what is the probability that this chord would be longer than a side of the inscribed triangle? This seemingly straightforward probability question leads to a perplexing result. The answer depends entirely on how we define randomly select. Different reasonable methods of random selection yield different probabilities. Method 1. Choose two random points on the circumference and draw the chord connecting them. Analysis shows the probability is 1/3. Method 2. Choose a random radius, then a random point on this radius, and draw the chord perpendicular to the radius through this point. The probability becomes 1/2. Method 3. Choose a random point anywhere inside the circle and draw the chord with this point as its midpoint. The probability is now 1/4. This is Bertrand's paradox, formulated by Joseph Bertrand in 1889. It demonstrates that the concept of random in continuous spaces requires careful specification. There's no single natural way to randomly select geometric objects. The paradox challenges our intuitive understanding of probability and randomness. In discrete cases like dice rolls, randomness has a clear interpretation. But in continuous geometric settings, different random procedures can yield systematically different outcomes. Modern probability theory resolves the paradox by recognizing that we must explicitly define the random process and its associated measure. The paradox isn't a logical contradiction, but rather a reminder that probability statements are meaningless without specifying the underlying random process. The Barber Paradox. Think about the natural numbers, 1, 2, 3, and so on. We can often describe or define these numbers using phrases in English. For example, 1 is the smallest positive integer. 7 could be defined as the number of days in a week. 2 is the first prime number. Some definitions are shorter than others. 1 takes just one word. The smallest prime number takes 4 words. Now, consider all the possible definitions we can make using a limited number of English words. It seems plausible that some numbers might require very long definitions, while others can be defined concisely. Let's focus on definitions using a specific length limit. Consider this phrase, the smallest positive integer not definable in fewer than 15 words. Does this phrase successfully define a specific positive integer? Let's assume it does. Let's call the number it defines b for Barry. By its very definition, the number b has a specific property. It cannot be defined using a phrase containing fewer than 15 English words. Any definition for b must use 15 words or more. But now, look closely at the phrase we used to define b, the smallest positive integer not definable in fewer than 15 words. Let's count the words in that phrase. There are 14 words. So we have defined the number b using a phrase containing only 14 words. This means b is definable in fewer than 15 words. But this directly contradicts the defining property of b, which was that it cannot be defined in fewer than 15 words. We seem to have reached a contradiction. The number defined by the phrase violates the very condition used to define it. Where does the logic go astray? The Barber Paradox highlights the inherent ambiguities and potential for self-referential loops within natural language, like English. The core issue lies in the vagueness of the term definable. What exactly constitutes a valid definition? Does the definition need to be unique? Does it depend on context? Does the specific vocabulary and grammar allowed matter? Can a definition refer to the properties of definitions themselves within the same language? The phrase definable in fewer than 15 words relies on an intuitive but not rigorously specified notion of definability within English. Natural language lacks the precision of formal mathematical languages. In formal mathematics and logic, paradoxes like this are typically avoided by using precisely defined formal languages where the rules for forming definitions are strict. Carefully distinguishing between the object language and the meta-language, the Barber Paradox mixes these levels, restricting the kinds of self-reference allowed, preventing properties from being defined in terms of the entire system of definitions they belong to. So the paradox doesn't reveal a flaw in numbers or logic itself, but rather the fuzziness and potential for self-referential inconsistency within informal natural language when we try to talk about concepts like definability. The Barber Paradox is a charming reminder that language, our everyday tool for thought and communication, can be slippery. Its flexibility allows for creativity, but also opens the door to these kinds of logical tangles. It playfully suggests that attempting to neatly categorize everything based on properties defined within the same system can lead to unexpected loops. The act of describing or defining can sometimes interfere with the property being described, especially when limits are involved. Think about labels or descriptions we use. Can defining something as indescribable sometimes inadvertently describe it? The paradox echoes this kind of linguistic twist. Let the phrase about the smallest undefinable number dissolve into the ambiguity of natural language. Rest with the gentle understanding that while our words strive to capture the world, they sometimes playfully trip over their own definitions, reminding us of the subtle dance between language, logic, and meaning. The interesting number paradox. Let's conclude our journey for tonight with a light-hearted, yet logically intriguing paradox concerning the very nature of numbers and their properties, the interesting number paradox. The paradox starts with a seemingly reasonable premise. Every natural number either has some interesting property or it doesn't. What counts as interesting? This is deliberately left vague, but could include properties like being prime, being a perfect square, being the sum of two cubes like Ramanujan's famous number 1729, being the number of planets in our solar system, appearing in Fibonacci sequence, and so on. It seems plausible that some numbers might be inherently dull or uninteresting, lacking any remarkable characteristics. Let's assume, for the sake of argument, that there does exist a set of uninteresting natural numbers. This set contains all the numbers that have no noteworthy properties. If this set of uninteresting numbers is not empty, then this set must contain a smallest element. That is, there must be a specific number which is the smallest uninteresting natural number. The property of being the smallest uninteresting natural number is itself a very interesting and remarkable property. It singles out that specific number from all others. So this number, by virtue of being the smallest one that is supposedly uninteresting, immediately acquires an interesting property, which contradicts the assumption that it belongs to the set of uninteresting numbers. This leads to a contradiction. If we assume uninteresting numbers exist, then there must be a smallest one, but being the smallest uninteresting number is an interesting property, meaning it cannot be uninteresting. Therefore, our initial assumption, that the set of uninteresting numbers is non-empty, must be false. The conclusion, there can be no uninteresting natural numbers. Every natural number must be interesting in some way. The interesting number paradox is a playful example of a self-referential paradox, leaning on the ambiguity of the term interesting and the well-ordering principle of natural numbers. Is it a serious mathematical paradox? Not exactly. It's generally considered more of a humorous observation or a metamathematical joke because the definition of interesting is subjective and not formally defined within mathematics. If interesting were given a precise, finite, and checkable definition, the paradox would likely dissolve. However, it charmingly highlights the power of the well-ordering principle. Any non-empty set of natural numbers must have a smallest element. This principle is fundamental and allows this kind of argument structure. The nature of properties. Natural numbers possess an incredibly rich tapestry of properties. It might indeed be difficult, perhaps impossible, to find a number that genuinely has no distinguishing features relative to others, even if those features seem obscure. Self-reference and subjectivity. The paradox works because the act of identifying the number based on its lack of interest becomes, itself, a point of interest. It plays on the subjective nature of what humans find noteworthy. The paradox leaves us with a smile and perhaps a newfound appreciation for the potential uniqueness hidden within every number, no matter how mundane it might seem at first glance. It suggests, in a whimsical way, that the realm of numbers is inherently fascinating through and through. Let the concept of the smallest, uninteresting number playfully contradict itself and fade away. Rest with the gentle, reassuring thought that perhaps, in the vast infinite set of numbers, each one holds some spark of interest, waiting to be discovered.